I was thinking about some of the questions that I've been getting lately from my students. And this seems to be the season of electrochemistry and redox reactions. And when we're doing those kinds of problems, it is very important that we start out with this one thing, and this is assigning oxidation numbers. This is not always straightforward. So we want to go through some techniques to do this and get it right every time. So one thing that's really helpful is to have some knowledge of elements and what their common oxidation numbers are. And oftentimes it's good to refer to the periodic table. So you know what? I think I'm going to go grab my periodic table and let's look at it together. This is a periodic table I've shared with you before. I like this one. It's perfect for YouTube because it's small. Do you like my little molecules, by the way? I love the shadows. But maybe I should do another molecular structure video. Use the models. I do have a Vesper video if you need to review molecular geometry. But today, redox chemistry and assigning oxidation numbers. So if we look at the periodic table and we think about group 1 and what we know about it, what we know is that all of these elements have one electron in their outermost shell. And what that means is that these will, when they get ionized, they will always be +1 for these metals, lithium, sodium, potassium, etc. Hydrogen is in group 1, and it can be +1. But when hydrogen is acting more like a non-metal and combining with other metals, then it actually gains an electron and becomes hydrogen -1. A few other common ones that we can count on are group 2, these metals, +2, very reliably. Aluminum +3, very reliably. Fluorine becomes -1 when it's combining with other elements. And this is related to it being so electronegative. The most electronegative element on the periodic table. And then oxygen. Here's another one we can usually count on. It is almost always -2. Gains 2 electrons to have its octet and have the same number of electrons as neon. But occasionally we see that it is in a peroxide, and then it can be -1. So just watch out for the peroxides, and if it's not a peroxide, then you can count on it being -2. So the rest of the elements can vary somewhat, but if we know just a few of those, we can then calculate most oxidation numbers. So I would say the best way to go about doing this is by doing some examples. So let's just do a bunch of examples, and this way I can show you some of the techniques. So let's look at sulfur dioxide. So when we have a whole molecule that is neutral, we know that all the oxidation numbers of each element have to add up to equal 0 because the molecule is neutral. So if we keep that in mind here, then we can assign oxidation states starting with the one that we know, which is oxygen. So the way I do this is I set up a little equation below or on top of the formula where I put the known oxidation number for whichever element that is, in this case, oxygen. As I said before, almost always -2. And then we have to multiply that by however many there are. In this case, there's 2 oxygens. Now, as I said, these 2 oxidation numbers for all the elements, they all need to add up to equal 0 because it's a neutral molecule. But the sulfur, we don't know what that is. So I'm just going to call it X. And now we can solve for X. What must it be to add up to give 0? So you can either do this by inspection, or if you're not 100% sure, you can go ahead and do the algebra that you would need to do. So here we multiply -2 times 2, and we get 4. And then when we add 4 to both sides, we see that X is 4. Now, I'm going to put +4 here because when we're assigning oxidation numbers, they will be either a positive number, 0, or negative. So, if this were a math problem, we'd just write 4, but since it's an oxidation number, it's +4. So, I'll just write it up here. Oxidation number of sulfur is +4, oxidation number of oxygen -2. Okay. Let's look at a case where we have a ion, such as a polyatomic ion. And I'm going to show you here that sulfur is a little bit fickle. And it has different possibilities for what its oxidation number is. So let's look at the sulfate ion and what we do here. So just like we did over there, let's set oxidation number for sulfur as X. And that needs to add up with all of the oxygens, each of which we expect to be -2. Now there's 4 of them. And these will add up to give not 0, because it's not a neutral molecule, but instead it's an ion. So this adds up to equal -2. By the way, if you're wondering why I wrote 2 minus instead of -2, that's just an alternate convention. So I could have written -2 there. It would be the same thing. Okay, Okay, so we can go through the same process here. Multiply through. And now we have a -8. And when we add the -8 to both sides, we end up with oxidation number of +6 for sulfur when it's in sulfate. Okay, hey, we're on a roll with sulfur, so why not continue? There is another polyatomic ion, but I'm going to, instead of making it an ion, since we just saw an example of that, I'm going to show you a compound that has 3 elements in it. So this is called Potassium Thiosulfate. Alright, so here we have more different elements to work with. But once again, we can look at first those that we know. And if at first we're not sure what potassium would be, we can bring in our periodic table. Okay, we look up. Where is potassium? Oh, here we go. It's in group 1. So we can reliably say it will have an oxidation number of +1. It will lose that 1 valence electron. Okay. So here we can say, alright, potassium, you are +1. And there are 2 of you. Okay. Now we will add that up with the oxidation number of sulfur. We're going to call this X again. But now we need to take note that there are 2 of these sulfurs. So instead of writing X here, I'm going to write 2X. 2 sulfurs. Okay, and now we'll add in oxidation number of oxygen, -2. And there are 3 of them. So we have to multiply that by 3. This is a neutral compound, so these will all add up to equal 0. Alright, so how about we multiply this out? Here we have +2. 2x. Here's our -6 equals 0. Now we can subtract 2 from both sides and add 6 to both sides. Okay. And just in case, if you need practice with algebra, why don't we do this one step at a time? Subtract 2 from both sides. Get rid of that 2. Makes that -2. Then we add 6 to both sides. And that gives us +4. And now we need to divide both sides by 2. And that gives us +2. So look at this. Sulfur in this compound is +2. In this compound it's +6. In this compound it's +4. Okay, and I just can't resist. I need to do one more with sulfur. Okay, let's do calcium sulfide. So at this point, it's very clear that we can't always reliably say sulfur is going to have any one particular oxidation number. But if we bring back our periodic table, we do see calcium being in a group 2 will have an oxidation number of +2. So if we say, all right, +2 +6, neutral compound, so we can see, and you might have even been able to do this just by inspection and say, must be -2. And that does make sense if we look at where sulfur is on the periodic table. It is right below oxygen, so it would follow that it is not surprising that sulfur could gain 2 electrons to have its octet and have the same electron configuration as argon. Okay. All right. I'm gonna do one more. You're like, you keep saying that. You keep saying you're gonna do one more, and then you keep doing more. Well, I just thought of something, because I haven't mentioned one of the rules of oxidation numbers, and that is for an element in its standard state, just an element by itself. And sulfur, the way it exists in its elemental form is as S8. It's actually a really cool little compound. It looks like a crown. I'll try to sketch it. Oh my gosh, I don't know if I can do this. I'll try it. So it goes kind of up and down, this sort of pucker type way. Let's see. There's 8 of them. Okay, I've already made 4. So I'm going to have to go. Oh my gosh, I don't think I'm. Squeeze it in. I'll try. Okay, 1, 2, 3, 4, 5, 6, 7. There needs to be another one. I'll put it here. Yes. Oh, it's gonna work. Okay, good. Yeah. So it makes a ring. So here I did kind of a side view, but if you looked straight down, bird's eye view, it would look a little bit more like an octagon. But anyway, this is how sulfur exists as an element. And whenever an element is just by itself, neutral, not an ion, then its oxidation number is 0. So that's for any element, that's true. And this is a really cool, unique element, and that it's a S8. A little bit more common is to have diatomics, such as O2, there's quite a few. I won't write them all down, but F2, Cl2, okay. These are also all oxidation number 0. metals and noble gases. These are monatomic, meaning they're just by themselves. So if you see something like iron or xenon or something like that, those also oxidation number of 0. So those are the most common scenarios that we see. So sulfur is unusual in that it exists as this S8. Phosphorus is also an interesting one. It exists as P4 in one of its elemental forms. Alright, well, I hope this was very helpful for you. I tried to give all the various types of scenarios that will help you assign oxidation numbers for whatever kind of compound you're looking at. So thank you so much for your patience for these weeks off while I've been healing, and I assure you that I will be making more videos from now on, as much as I can. So as always, give me your requests, and I will be talking with all of you really soon.